Welcome. Today we will discuss indirect vector control or feed forward vector control. Of indirect or feed forward vector control of induction motor. So, the main point about indirect vector control is the unit vector, that is e to the power j theta e, is generated in feed forward manner. In previous class, we discussed direct vector control, in which the unit vector is generated from feedback signals of voltage, current and speed. So, that was feedback vector control, but in this case unit vector is generated in feed forward manner using the slip relation, slip speed relation. This indirect vector control is very popular in industrial drives. So, the principle can be understood from the phase orientation diagram. So, here we have the beta axis, alpha axis is 90 degree behind, alpha beta stationary reference frames, and we have the flux components psi alpha r and psi beta r, alpha beta components of the rotor flux psi r hat, which is same as psi d r, because the d axis has to be along the rotor flux psi r. The d axis and q axis, they are rotating at synchronous speed omega e. So, q axis is 90 degree ahead to d axis. This is the synchronous rotating reference frame rotating at speed omega e, dq reference frame. So, that the angle between d axis and alpha axis is theta e. This is the angle theta e, where the speed of the reference frame omega e is d theta e by dt. And then the essential fact about vector control is the stator current component along stator current component IDS is oriented along the rotor flux psi r. This is the IDS. This is the one IDS, and this is the IQS, q axis stator current, and this is the stator current vector IS. And so that we have I beta s along beta axis and I alpha s along the alpha axis. Then we have also a rotor axis. This is the dr axis fixed on the rotor, so that it is moving at speed omega r, and this angle is between alpha and dr axis is theta r, and angle between dr and d axis is theta s l. So, and also along the q axis psi q r is 0. So, this is the phasor orientation diagram for indirect vector control. So, we have the dr qr is the rotor reference frame, fixed on the rotor, and hence rotating at speed omega r. The slip speed omega s l is omega e minus omega r. So, rotor speed is omega r, the speed of the reference frame is omega e, the difference between omega e and omega r is the omega s l. So, that corresponding to omega s l, we have the angle theta s l. So, that omega s l is d theta s l by d t, and omega r, the rotor speed is d theta r by dt. So, for this, the angle theta e which is integral of omega e dot dt, that is integral of omega e is omega r plus omega s l, integral is theta r plus theta s l. This is the first equation which will be used for indirect vector control. For vector control, the current component IDS is to be aligned on rotor flux psi r which is also the d axis. Current component IQS is to be aligned perpendicular to rotor flux psi r, that means q axis. So, next derivation of control equations for indirect vector control. So, from the discussion of the machine equations, induction machine equations in the reference frame, synchronous rotating reference frame, we have voltage across the DR winding is VDR, that is resistance drop due to current IDR, plus transformer EMF is d psi dr by dt, minus rotational EMF is omega E minus omega R into psi q r, and voltage along the q axis rotor winding VQR is R resistance drop due to current IQR, plus transformer EMF is d psi qr by dt, plus rotational EMF is omega E minus omega R into psi dr. Rotational EMF due to d axis flux is positive because it is the back EMF nature, and hence opposing the applied voltage, and voltage rotational EMF VQR due to psi QR is negative. And for motor operation, rotor circuit is closed, rotor winding is closed, so that VD rotor voltage is 0, so VDR and VQR are 0. Then we go to these flux linkage expressions. The rotor flux linkage psi dr along the d axis is given by LR into IDR plus LM into IDS, and rotor flux along the q axis is psi QR, that is LR into IQR plus LM into IQS. So, from these two equations we get the rotor current IDR, that is 1 upon LR into psi dr minus LM by LR IDS, and rotor current IQR is 1 upon LR into psi QR minus LM by LR IQS. As rotor currents are inaccessible, IDR and IQR cannot be sensed or measured. Eliminating IDR and IQR from the rotor voltage equations, we get d psi dr by dt plus RR by LR psi dr minus RR LM by LR IDS minus omega SL psi QR is 0, and q axis, from the q axis voltage we have d psi QR by dt plus RR by LR psi QR minus RR LM by LR IQS, then rotational EMF is here plus omega SL into psi dr, and this is 0. So, this is equation 2, this is equation 3. So, for vector control, what is required? For vector control, it is essential that psi QR, q axis flux must be 0, its derivative should be also 0, d psi q r by dt has to be 0 and d axis flux psi d r is the total rotor flux side r. This is essential for vector control and this is equation number 4. Now, substituting equation 4 in equation 2 and 3, we get, and simplifying, we get L r by r r d psi r by dt plus psi r hat is L m into I d s. This is equation 5 and the slip speed omega s l is given by r r L m by L r I q s by psi r hat. This is equation 6. From equation 5, at steady state condition, psi r hat equals to L m into I d s. And most important, indirect vector control is obtained by implementing equations 1, 5 and 6. Using these 3 equations, we can implement indirect vector control. Next we will discuss a scheme of indirect vector control. So let us consider example of position servo. That means we have position control. So we have, first we have the position system, servo system. So we have the position command psi r star. Then subtract from it the actual rotor position theta r. It goes through a position controller. Position controller output is the command rotor speed omega r star. Then subtract from it the actual rotor speed omega r. Then the speed error goes through a speed controller. And speed controller output is the current IQS star, torque component of stator current command value IQS star. Then we also take this speed this is a flux weakening control algorithm scheme which takes the omega r star and generates from it the rotor flux command psi r hat star. This goes through a flux controller. And flux controller generates the command value of the flux component of the stator current I d s star. This goes to vector rotator command value of the current I d s vector rotator and 2 phase to 3 phase transformation. Okay. So, in the power circuit, so okay, this 2 phase to 3 phase transformation, it will take the unit vector cos theta e and sin theta e and generates the current commands I a star 3 phase current commands I b star and I c star. Then we have a comparator in which we subtract actual motor currents I a, I b, I c from the reference currents. Then we will go to the power circuit. Power circuit consists of a diode rectifier at the front end, which gives the DC supply for the PWM inverter. This is the PWM inverter. So, PWM inverter gets filtered DC supply from the diode rectifier. So, this is the capacitor filter CF which filters the ripples in the output diode rectifier output. Then in this circuit a dynamic braking resistance is included. This is the braking resistance RB which gives dynamic braking. So, PWM inverter uses, let us say, because you have in this case we are showing hysteresis band PWM current control, hysteresis band PWM current control, which gives the control pulses to the PWM inverter, and PWM inverter is feeding the induction motor and we have the current sensors, for the 3-phase current sensing. So, we have filters if required, which gives the filtered currents. So, and for the vector rotation, the unit vector theta e is required. How it is generated? It is generated from the command value of the flux torque component of the current IQA star and the rotor flux peak psi r hat. So, what it does? We have a transfer function R r L m by L r into psi r hat. This is multiplied with the IQS and generates the command slip speed omega SL star. Omega SL star. With this, rotor speed is added, omega SL star plus omega r is the omega e. Then we have one integrator which gives theta e, and we have a lookup table which gives cos theta e and sin theta e, the unit vector. Then for indirect vector control, an incremental position encoder is essentially required, incremental position encoder, which gives theta r information, incremental position encoder theta r information, and theta r information, and also by putting a d by dt we get the rotor speed omega r. So, this PW inverter, let us show a DC supply for this. We have a DC supply here, VDC for the PW inverter. So, first thing is, because it is a position servo, position command is there and actual position is taken feedback, and position controller generates the speed command, and speed feedback is obtained from the position information, and speed error is goes through a speed controller which generates the torque component of the current IQA star command value, IQA star, and then command value of the flux component of the current IDA star is obtained from a flux controller. Flux controller and flux command value is obtained from the speed command value through a field weakening control algorithm, and then actual flux is also considered, so that a flux controller generates IDA star. These are the two command components, IDA star and IQ star, and it is converted to dq to alpha beta using the unit vector cos theta e and sin theta e. How that theta is obtained? IQ star is taken again, and from it is multiplied with a function RR LM by LR by psi r hat, which generates the command slip speed omega SL star. So, previous equation we have got. Then speed field is added, rotor speed is added with omega SL star, and we get omega E, which is integrated to give theta E, and look up using a lookup table, unit vector components sin theta e and sin theta cos theta e are obtained, which are used for vector rotation in the control scheme. And from that we get IA star, IB star, IC star 3 phase command currents from the DQ command currents, and actual motor currents are sensed and taken feedback, filter will be there. So, actual IA, IB, IC are subtracted from the reference corresponding reference current commands, and current errors goes through a hysteresis band PWM current control, which generates the pulses for the PWM inverter. And in the power circuit, a filter capacitor is used to filter the diode rectifier ripples, and a braking resistance is used. So, how the in normal operation PWM inverter supplies the motor induction motor the rated voltage at rated frequency, and supply controls the phase of the current also, so that vector control is obtained. Now, suppose motor operation is to be changed, speed is to be reduced, motor speed is to be reduced from the present speed. So, in that case, the first thing, because torque has to be negative, so IQA star is made negative. Torque command IQA star is becomes negative for negative or braking torque. When IQ star becomes negative, in omega SL star also becomes negative, because IQ star is negative, slip speed command omega SL star is also becomes negative. When the slip speed is negative, the omega E synchronous speed will be less than omega R. So, braking torque is braking action is obtained, because magnetic field is rotating behind the rotor, it is the generating action. So, induction motor operates as a generator. So, regenerative braking is obtained, and current direction reverses, current phase reverses, and flows to the from inverter to the DC link. So, and this will lead to charging of the capacitor CF. Capacitor CF gets charged. When capacitor charge exceeds a specified upper limit, it should not be overcharged. So, by closing the switch S in across the DC link, the dynamic braking resistance RB is brought into action. So, the generated energy is dissipated in the dynamic braking resistance RB. So, this way speed is reduced. When speed reduces and again becomes less than the new becomes less than the synchronous speed, it motor rotates at steady state at the new value of speed. So, this is the braking action. So, though we have shown only hysteresis band current control, This hysteresis band current control can also be replaced by synchronous frame current control synchronous frame current control and most important is below the rated speed the flux is constant as usual, flux is constant and rated value flux is constant at the rated value giving the constant torque operation. For speeds above rated speed, field weakening control is done at constant power mode with closed loop flux control. So, with this we will go to current control. Current control in vector controlled drives. So, some salient points, both direct vector control and indirect vector control require instantaneous current control, that is important, very fast response. Instantaneous current control of the inverter. So, as I have mentioned, hysteresis band current control is often used, but hysteresis band current control harmonic content is not optimum. With hysteresis band PWM, harmonic content is not optimum. Then another demerit is at high speeds current controller tend to saturate. Because of higher back EMF or counter EMF. So, when the current controller saturates in part of the cycle because of higher back EMF, fundamental current magnitude and phase. We will lose tracking of the command current. So, vector control will not be valid. So, synchronous current frame, synchronous current control. Synchronous current control means stator current in synchronous reference frame. In synchronous reference frame, the stator current is DC, direct current. So, when synchronous frame current control is used, the synchronous current control assure amplitude and phase tracking of currents even when PWM controller goes to overmodulation range. We will see the scheme of synchronous frame current control. We have the command value of the flux component of the current and subtracted from it is IDS, and we have a proportional control, say K1 plus K2 by SPI controller. Then we have that command torque component of the current IQS star. IQS is subtracted from it, and passes through a PI controller, same. So, these IDS and IQS for feedback are obtained from 3 phase to 2 phase and inverse vector rotation. So, it takes the currents IA, phase currents IB and IC. It also takes the unit vector cos theta e sin theta e and generates IDS and IQS. Then we have the flux components psi beta s and psi alpha s. Alpha beta components, stationary reference frame components of the stator flux, and it is inverse vector rotation using the unit vector e to the power j theta e. So, it gives psi q s and psi d s from alpha beta to dq transformation using e to the power j theta e. With psi q s we multiply the frequency omega e and we get omega e psi q s. Similarly, with psi d s also omega e is multiplied and we get omega e psi d s. So, we have that this is the d axis current IDS loop, and within the IDS loop omega e psi q s is subtracted, and what you get we get is V d s reference value. Similarly, this is the q axis loop IQS loop, and in the q axis loop the EMF omega e psi d s, the count back EMF is added, and we get V q s star. And here we have vector rotation and 2 phase to 3 phase transformation, which gives V A star, V B star and V C star for voltage PWM. To voltage PWM inverter. Okay. So, and here this also requires the unit vector e to the power j theta e for vector rotation. So, in this case in the d axis loop IDS loop, d axis current loop IDS loop, the back EMF omega e psi q s is subtracted to get the V d s star, and in the IQS loop the back EMF omega e psi d s is added to get V q s star. So, this is the back EMF compensation. Back EMFs are omega e psi d s and omega e psi q s, this compensation. is used to get the command value of the voltages, and this goes to a sinusoidal PWM inverter, pulse width modulation inverter to get the control voltages VA, VB, VC command values. So, in this case we have introduced the feedback loops. Feedback IDS, IQS loops bring with it a small amount of coupling. So, to enhance the loop response, feed forward, back EMF compensation. Back EMF compensation means omega E psi ds and omega E psi qs. Are included in respective loops. In IQS and IDS loops. So, this DC current control with back EMF compensation assure the command current tracking. Over a wide range. Over a wide speed range and even in overmodulation. So, this has the advantage synchronous frame current control, the DQ current control of current enhances the performance and prefers compared to hysteresis band PWM current control. So, this is important. Thank you for attention.